So what's the idea behind a transducer? So let's say there's some sort of energy source in the universe, okay, and that energy is maybe we modulate it as a human, right, to convey information. A good example of this would be sound, right? So if there's a person over here, I don't know, talking to you, okay, and their vocal cords are actually, pushing and contracting and everything, and they're basically, adding energy to the air, right? And this energy, this energy wave, right, is flowing through the air. Can we add a device, right, which can take that energy, that energy variation over time, and if we were to plot this, right, so where this energy exists in what sort of form? It's going to be actually pressure. So if we were to, over time, plot the pressure of the air, we'd see something like this, right, as someone speaking. And the idea of a electrical transducer, so this would be a acousto-electric transducer, is to take that energy wave and convert it into a digital, or into an electronic signal. So instead of pressure varying over time, we're going to now have voltage varying over time. All right? And this is, of course, a device like this is usually known as a microphone, and we'll deal with those in Lab 7 in the class. But once you can take one form of energy and convert it into an electrical form where basically voltage varies over time, this is where we can start doing stuff with it. So you can imagine you have the Raspberry Pi, and it's measuring those voltage, the level of that voltage, right? And when it goes above a certain amount, maybe it makes a decision. When it's under a certain amount, maybe it makes a different decision or something. Okay, and I mean, and what does that decision mean? It could mean you do a certain image on the screen, or you turn on a light, or whatever. Okay, so signals like this, so like sound and all those things, these are what are known as analog signals. Okay, signal. All right, and this is also analog electronics. And we won't deal with that right away in the class. We will later on. But it's the idea that, a voltage can take on many values, right? This right here might be, I don't know, 3.0 volts, and this might be, 1.0 volts, and this might be 1.4214 volts or something. Who knows, right? And hopefully these at least somehow, like the sign of a good transducer is usually that, these values in volts linearly correspond to maybe the pressure values over here. So maybe this is 10 kilopascals or something, and this is, 3 kilopascals. I don't know. I'm just saying. But the idea is you have these devices which take one energy form and convert them to another. This is known as a transducer. Now, what would happen, though, so if we were to actually plot out all of these numbers over time, right, maybe you'll have 3.0 volts, and you'll have, 1.421 volts, and you'll have 1.0 volt and 2.0 volts and all these things, right? There's information in these, right? And ideally, in an ideal world, we'd get that information and be perfect. But in real life, what happens is you have noise, right? You have, a fan or something in the background, right? And that's generating its own sound, which is then messing this up, right? And then that ends up causing problems with, the pressure, actually. And then your voltage reading gets noise on it as well. Okay, and then it becomes harder to actually discern what's the voice compared to what is the fan or what is the other junk. And not only that, then there's electrical noise, right? Like everyone in your house where you're at, if you're in the United States or in the Western Hemisphere, we all have power plugs that look like this, right? And then a cord will, go into it, right? And there's a prong, and then usually this goes in here, whatever. But these things have about 60 hertz. I mean, they mostly in the U.S. and Western Hemisphere run at 60 hertz, okay, which means that the electricity in them is running back and forth 60 times a second. All right, and what that means is actually they're acting like big giant noise, like electrical noise things. So a microphone circuit like this right here might be getting bombarded by the electrical noise from the wall. This is known as mains noise, and so then that's getting thrown on top of your audio signal. And then if you bump the wire, then there's more noise that comes in, and then it messes things up, okay? So there's lots and lots and lots of noise that can sometimes happen whenever you have transducer circuits, which can make it very hard to get meaningful information out of them. That's an inherent problem of analog signals, and there's lots of work, and people have we figured out ways to deal with it, but at the end of the day, there's only so much you can do. If you have too much noise, your signal goes away. Okay. So one way to get around it is actually the idea of known as digital electronics. Okay. And so we have analog. What are Digital electronics. Digital signals, digital electronics, etc. So what's the idea here? It's the idea that you break the world down into high and low, yes and no, on or off, okay? So it's a way of viewing the world and of building electronics and handling signals where they can only be one of two states. All right, and the idea is maybe there's some event in the universe. That's a big x-axis. Let me shrink that. So over time, right? And maybe there's some, again, instead of, let's go with sound again. Okay, so there's someone talking or whatever, right? And, no, that's a bad one. Let's go with a light bulb conveying information. So you have some sort of light source right here. I don't know. Yay. Okay, and it's beaming out light. Let's actually make this nice and... Okay, and that can go on or off. All right, and we can use, by turning it on or off, we can actually, send information. So maybe this is the illumination intensity. And over time, what does a plot of that look like? Like this. Something like that. So maybe if you're just sending one, on, off, on, off, on, off, on, off. Now, if all you are caring about on the other end is determining if you're on, off, so maybe you have some sort of photoresistor or photodetector, which we'll be working with right here, and that's picking up those signals, right? We'll probably be able to get that signal in pretty good, right? Right, so that'll be good. Now the benefit of digital electronics, why it's so nice is, let's say you have I don't know, some sort of other light source over here, right, and that's shining down. It's going to add in noise, right, to the system. So maybe it's I don't know, doing its own thing. Okay, and then that's going to, of course, get picked up on your receiver side right here if you're trying to, maybe send a secret message. So it's, that's here. You can't get rid of that really. Or sometimes you can, but not necessarily. Okay. But the neat thing, what digital electronics cares about is, it's not so much what the exact value is. It's really more, am I above or below a certain level? Okay. So we could say down here, let's call this the low region for signals, okay, and up, let's pick green. Up here is our high region of signal. All right, and the same thing over here. So anytime digital signals at the end of the day are really just derived from analog signals. It's a different type of way of reading and generating analog signals, where you care less exactly about the amount and more just, is it within a certain region? And so over here, we're turning on our flashlight and turning off our flashlight as we go through our life. And even though we're adding in noise, we're still staying in the low region. So maybe we're actually trying to send a 0. I'm going to do 0 for low, 1 for high. So we're sending a 0, 1, 0, 1, 0, 1, 0, 1, 0. And then over here, we're picking it up to 0, 1, 0, 1, 0, 1, 0, 1, 0. Now, even though there's noise, there's other additional signals on here, right? So maybe it's not this is 1.1 and then 1.2 and 1.3, whatever. Because maybe we have some sort of dividing line where we're saying, okay, any signal below 2.5 volts is a 0, anything above is a 1. The noise doesn't affect it, okay? We still just send a 0, we still send a 1. And on this side, more importantly, we can actually still determine, oh, this was a 0, this was a 1, this was a 0. And so there's not as any confusion. Because before, with our analog signals, right, if the information is actually contained in the exact value of the signal, noise comes in and messes it up. And then it's really hard to back out what exactly we meant. So digital electronics are really about determining, it's dealing with the world in only ones and zeros, okay? And this we could say true, false. A lot of times just TF. Okay, yes, no, on, off. Very often we do 1, 0. Okay, all of these are a binary or digital view of the world. Okay, there's only one way or the other way. Okay, very, very well defined. All right, now this seems kind of magical, right? Like if we can get by in our life by only sending ones and zeros or ons and offs, we can be a little bit more robust to noise. Now, I do want to add the caveat, right? If you have too much noise, right? Like maybe if there's a nuclear bomb that goes off over here and it just adds like a lot of light noise, right? There are limits, right? If you had too much noise, the system's messed up and it's gone forever. But within certain limits, we can get by. Now, what's the downside of this digital thing, right? Like, why don't we? I mean, like, is it just free? Is it free goodness, or is there actually a cost? And the issue is, yeah, it's actually digital. Like conveying information digitally can be slower than whenever you're doing it with analog. If you think about it, right? Like, let's say you wanted to specify to your friend what song to play. Like maybe let's say you had 1,024 songs. Okay, whoops, let's use black. So let's say you had 1,024 songs in your whatever pod music player, okay? And you wanted to tell your friend what song to play as quickly and as most efficiently as possible, okay? Now, one way you could do it with analog, right? Maybe you have a light source and you have pre-calibrated transmitter and receiver, right? And you have one of 1,024 at different light bulb intensities that you're sending over. So maybe this is a plot over, many hours, and you're sending your friend like, okay, I want to play these songs, something like this. Who knows, right? But each voltage value in here, and maybe you've chopped up your voltage range, your light intensity range into 1,024 different values, okay? So what you can do is you could actually tell, or maybe let's pretend you're actually sending a playlist, okay? And so you can do it really quickly. You can say, oh, I want to play song 34, and then 68, and then 1,000, and then 500, and 200. And so you can basically send that in analog very, very quickly to your friend, who will then, they have a perfectly, calibrated system, will be able to know, oh, I got this signal, and then this signal, and then this signal, and then, whoops, this signal. And your friend will know, okay, these correspond to certain songs on my iPod thing, right, with the dot thing. I don't know. But anyways, earbuds. Okay. And then they know how to play the songs really quickly now. Now, we just talked about, though, right, this is an analog approach. And there can be the downside, though, where if at the same, point in time, maybe the sun's coming up or something, and it adds just a little bit of fringe of light noise onto your transmitter's signal, right? All of a sudden, instead of like your friend over here, it gets in a 33, they can't be sure if that's actually supposed to be a 34 or a 32 because there's a little bit of sun hitting the signal, right? And then you're like, uh-oh, right? And this is where digital electronics come in, right? You're only going to send ons and offs, right? But how do you send 1,024 songs to your friend, right? If you can only send a yes or no, what do we do, right? You can go, okay, low, high, right? And your friend will try to, basically you can only send two things, right, with digital, right? So if you have a 2-song playlist, you're good. How would you send 1,024 songs? Well, in digital, what you end up doing, instead of encoding the information in the amplitude, you actually encode it sort of in time, in a sense. All right. And so we come up with these sort of ways of representing numbers and values using ons and offs, okay? So ones and zeros. And this is where the idea of binary comes in. This is actually why all modern computers use binary. Binaries are base 2 numbers. So you go from 0 to 1 to 1 0 to 1 1 to 1 0 0 to 1 0 1, on and on, this is base 2. In base 10, these would correspond to 0, 1, 2, 3, 4, 5, on and on and on. So the idea behind binary, and the reason we use it in electronics and digital electronics, and pretty much most modern electronics, is because digital signals provide us this really nice level of noise suppression, right? We can actually really clearly convey to a friend via a transmitter and a receiver a 1 or a 0, but we need to be able to represent more than just 1 and 0. So what we do is we end up saying, okay, for the next, minute I'm going to send a binary number to you, and let's say I wanted to send 101011 or something, right? What I would end up doing is going and saying, okay, I'm going to send a 1 and then a 0 and then a 1 and then a 0 and then a 1 and then a 1. All right, and then my friend, even if there's noise in the system and they actually pick up something that looks like this, right? They can still go, oh, you know, we're fine because up here is, whoops, up here is my like 1 region, and down here is my 0 region or something. So I can still figure out, oh, 1, 1 0 1 0 1 1. Now there's a little bit more of an agreement you have to wait on. In particular, you have to be going, okay, every maybe some sort of, I don't know, every second, so 1 second long is 1 digit. Okay, so then this would take, and your friend and you have to agree on that. You have to say, okay, I'm going to send 1 different value every second. So your friend, and that's how you could discern between simply a 1 or a 1 1, right? So you each have these clocks going on, and this is actually the clock rate of the digital system, right? And this is where, a lot of times you'll hear, oh, the iPhone has a 1.2 gigahertz processor or something. So that gigahertz term is referring to, well, giga is what? 1 e to the 9, or 1 times 10 to the 9, right? And hertz is cycles per second. Okay, so this is actually referring to the clock rate of the system, which means the digital system of your iPhone is, 1.4 billion ones and zeros per second. That's how it basically, the entire system synchronized like that. And so you can see there's a pro and con, like there's goods and bads here with this digital thing. We have really good noise suppression, but because of the fact that we need to spread out our information over time as opposed to analog where you can kind of do, pack a lot more into one moment, it may potentially be slower. Now, the good thing is digital electronics have like super sped up. Okay, so like an iPhone, I'm just guessing here, but if its processor is 1.4 billion, 1.4 gigahertz, right? That means, you can send 1.4 billion values of information down like a wire, okay? And that's pretty fast. You can send a lot of stuff in 1 second then. So if digital electronics are fast, they kind of offer us this great situation where we can very, cleanly send signals between different parts of a circuit, or, even, between different environments. But only if it's fast, right? If it's slow, it actually kind of, analog could sometimes be better. All right. So this is known as binary. And inside of computers, they actually represent all numbers with binary because all computer electronics are designed to work with just ones and zeros, okay, for the benefit of noise suppression. And so if we're thinking about like, some really basic binary events that we could be dealing with our Raspberry Pi. Let's do our Pi. One could be just turning on and off a light, right? This is a event which is either on or off. Okay, when it's on, it's glowing. When it's off, it's not. And this is what you're going to be doing in Lab 2, first of all, right? You're going to hook up some LEDs, and those LEDs are controlled by what are known as GPIO pins, okay? And this GPIO stands for General Purpose, I can't write today, Input and Output. Okay, what that means is those pins can be told to be either digital inputs or digital outputs on the Raspberry Pi. So when they're digital outputs, you can either tell them to be high or low, and you do that by doing something like GPIO.output. After you've set them up, keep in mind, the pin number, and then either true or false, or 1 or 0. All right, in Python, you can actually do either. If they're an input, on the other hand, what they're doing is kind of where the outputs are kind of a electrical mouth. They can, convey a binary signal to the world. Inputs are actually electrical ears. They're listening for an electrical signal right here, and they'll report it back to you in code. So you can do that by doing GPIO.input and then the pin number right here. And that will actually return back a value. So maybe we say, okay, X equals GPIO input of 23. That's going to give us whatever the electrical reading is at pin 23 and store it in the variable x. Now, of course, you have to make sure you actually set it up as an input, but that's how you do it. So for our circuit, what we're going to do is with our Raspberry Pi, for inputs, we're going to add a switch. And what this switch does is, it looks like this schematically. In a switch, all it is at the end of the day is a piece of metal, and a movable piece of metal. When you push down on it, right, this piece of metal connects and then electricity can flow. And when you don't push down on it, at least the switches we have, it's open. And so what we do in the Raspberry Pi, there's a line in the code which says, like, whenever you create the input pin and you specify it's a pull up, okay? And what pull up means is on the inside of the Pi, we're actually telling it that this pin, whenever it's left on its own, it gets by default pulled up to high voltage, okay? So the Raspberry Pi, its digital signals are 3.3 volts are high, or true, or 1, or whatever, and then 0 volts is low. So whenever you do a pull-up, what's happening is you're saying, okay, by default, this pin is high, and then if anything of any sort of electrical, if any other electrical signal comes in that conflicts with that, it's going to dominate. All right, and the reason we actually need to do this pull-up thing, set sort of a default value, is because if we don't do that, this switch right here, all right, so we have a wire coming off the Raspberry Pi and it's listening to an electrical signal. It goes to this switch part, right, and this doesn't connect anywhere. The other side of the switch goes to ground. So we can say very definitively, always this spot of the circuit is 0 volts, or binary 0, okay? But if this is an ear, okay, like an electrical ear right here, what is this spot in, whenever the switch isn't closed? If we're not actually specifying a default value to go to, it's undefined, right? There's nothing telling it what to be. Okay, so what we do is, whenever we say we default these to pull up, what we're saying is, okay, we're going to actually add a little bit of like really all it is actually a resistor on the inside of a certain amount, and it ties it to 3.3 volts. All right, so when nothing else is connected, this pin defaults to high voltage. But as soon as you close this thing and we actually complete the circuit, it goes back. It actually is 0 volts. There's also something called a pull down as well, which is the opposite, where the switch will default to 0 and then you can connect it to 1 through like a push action. But we won't be doing that in this class. You can if you need to, but we're not going to make a big deal out of it.